quantum image sensors measure light one photon at a time, making them well suited to operate in challenging conditions from very low light to ultra-fast motion. Here, we introduce probabilistic events, a new computational primitive for quantum perception that processes over 50,000 quantum frames per second on desktop-grade GPU hardware. This is up to 4 orders of magnitude faster than reconstruction-first approaches. Probabilistic events synthesize 3 complementary information streams: a temporal stability map, entropy changes that capture uncertainty or confidence, and a motion-aware flux aggregate. This representation bridges photons to perception. In this real-world example, from the same photon stream, it supports edge detection, depth estimation, and instance segmentation under strict latency and compute constraints.
Imaging systems allow us to gather data about the world around us. We're increasingly using computers to process this data, which opens up new capabilities. This presents the question of how to capture data for color photography, radio astronomy, lensless imaging, microscopy, and more. We answer this question using information theory. Specifically, we use the measurements from an imaging system along with a noise model to calculate mutual information, which we use to guide the design of imaging systems. For example, we can compare traditional and lensless imaging systems. We can show that mutual information is in agreement with reconstruction-based evaluation. We also use information-driven design to optimize encoders using gradient-based methods. Our approach predicts decoding performance, but only uses measurements, so we don't need ground truth data. As a result, it's broadly applicable. If you'd like to learn more, please visit our project website.
We present histostyle, histogram-guided stylization. Traditional photostylization tools lack semantic awareness, have hundreds of convoluted controls, and are notoriously labor-intensive. On the other hand, modern image editing models are fully automated, but suffer from hallucinations, poor controllability for expressing artistic intent, and inefficiency. When I prompt NanoBanana to modify only the lighting of a stagger photo, it still alters the structure of the image. Histostyle harnesses large models to hit the sweet spot between traditional tools and modern prompt-based editing. It takes the image and global user intent, then applies spatially aware edit that is constrained to be photorealistic. Histostyle is hallucination-resistant by design. It achieves real-time interactive speeds and uses histogram guidance for precise controllability. This clip shows how histogram sculpting controls the histostyle model in real time. Come to our poster to learn more.
Hi, I'm Hodaka Kawachi from the University of Osaka. We recover RGBD from a single coded defocus image. The task is difficult because blur mixes texture, depth, noise, and optical mismatch. Instead of training a network to directly regress depth for one fixed camera, we separate the physics from the prior. A calibrated coded aperture DFD forward model predicts how a candidate RGBD scene would appear as a defocused observation. A diffusion model provides a natural RGBD prior. At each sampling step, we predict a clean RGBD estimate, reblur it with the physical model, compare it with the captured image, and correct the estimate in X0 space before continuing diffusion. This gives stronger measurement consistency and reduces hallucination. The results show stable reconstructions across noise levels and real captures with our prototype camera. We are happy to discuss the X0 space update and real camera experiments at the poster.
Single-photon LiDAR measures the distance to a target from the time delays between pulsed laser emissions and single-photon detections. The extreme sensitivity enables sensing under photon-starved conditions. If the illuminated target is moving, the target's motion induces a Doppler shift in the pulse repetition frequency. We recently introduced a technique called Doppler single-photon LiDAR to estimate the velocity of a target from this Doppler shift, in addition to its distance and reflectivity. One limitation of that initial approach was the inverse relationship between the unambiguous range and the pulse frequency. In this work, we show how the velocity can be estimated for non-periodic pulse patterns, enabling both a long unambiguous range and high photon detection rates. We compare the trade-offs of different pulse pattern schemes in terms of the simplicity of implementation and estimation performance. Come see our poster or our recent Optics Express paper for more details.
Hello, I'm Sabit presenting mirror reflection understanding for feed-forward 3D construction. Feed-forward 3D models convert images to point map from a single or many view. With a mirror, the prediction becomes ambiguous. Master treats the mirror as a window, points land behind the mirror. Pi3 treats the mirror as a painting. Mirror resolves this with 3 point maps, transmitted, reflected, and the mirror point map. Reflection geometry links the three. From transmitted and reflected maps, we recover mirror points and the normal. We adapt master, replacing the point map head with mirror-aware heads. The idea can be extended to any other model. To create data, we procedurally place mirrors in existing scenes. With mirror, reflected points land in the real world. We extend global alignment so views of the mirror from different angles reconstruct the whole room. This carries to real-world captures as well. Beyond the point maps, we can get mirror masks and normals from mirror. Mirror outperforms baseline in both monocular and multi-view with the lowest error on transmitted, reflected, and with mirror matrices. Find us at the ICCP poster. Thank you.
Hi everyone, today I will be talking about quantile uncertainty training and conformal calibration for inverse problems. Deep learning has offered tremendous promise for scientific and medical imaging. However, they can result in hallucinations, which are hard to pinpoint and can have serious downstream consequences. For example, in this MRI knee image, the left image is the ground truth and the right is the model prediction. If I didn't draw your attention to the structural hallucination, it would take a while for human eyes to find. Finding areas of hallucination can be made easier by quantifying model uncertainty. You can see here in this uncertainty map that the red highlighted region corresponds to the hallucination. How do we get this map? We condition a single unit to predict an image as a function of the measurement in a quantile value Q, and in this way the network learns the entire conditional quantile distribution. To calibrate our bounds, we query initial upper and lower bounds and adjust them until coverage is reached. This results in learned bounds that are non-uniformly scaled with statistical guarantees. At test time, our method yields tighter uncertainty intervals and is faster and more efficient than deep ensembles. If you're interested in learning more, please stop by our poster. Thank you!
In recent years, 3D scene representations have greatly advanced. However, even the dynamic methods for volumetric scenes are limited to 60 frames per second. This is due to physical camera constraints. Purchasing multiple high-speed cameras isn't an accessible solution, as these cameras are costly and can experience fundamental data and bandwidth limitations. Previous computational imaging methods that achieve high-speed video require specialized camera hardware for capture, making these methods ill-suited for multi-camera scenes. We propose a new method for capturing a class of high-speed volumetric scenes from multiple cameras simultaneously, by strobing different colors of light at different times, allowing us to capture a high-speed scene at 60 frames per second and reconstruct it from novel views at 600 frames per second. Crucially, we use cheap, unmodified cameras with no significant data or bandwidth limitations at capture time. Here we show our ability to recover motion for multiple objects traveling along different paths. Now we show results from real captured scenes, first with a simple piece of paper with text, and now with multiple objects that have more complicated geometries.